Right. London forces, we need to know factors that affect them in order to answer our multiple choice questions correctly. All right, the shape of the molecule, the strength of dispersion forces. Long skinny molecules like N-pentane tend to have stronger dispersion forces than short fat ones like neopentane. All right, so pentane, what's the formula for pentane? Who knows?
That'd be pentane's 5.
C5.
H.
I heard it. Somebody said it. H12, because we know CN H2N plus 2. All right, so pentane, long carbon chain. All right, in this case, this neopentane, it's all going to be globbed up. This one's going to go in a straight line. This one's going to be across. All right, so when you have the carbons, 2 are going to stack on top of the other 2, and then you have 1 kind of coming out. All right, so you need to know, if you look at the shape, all right, the ones that are long and skinny, all right, which ones are going to have better dispersion forces? Neopentane or N-pentane? Tell me why. Why? Okay, very good. More surface area. Thank you. Ooh. Ooh. Yes. This is due to increase.
It's okay.
You're supposed to answer. You read already. Okay.
No, I do that.
All right. The increased surface area. Very good. It was in your packet too. All right. Factors affecting London forces. The strength of dispersion forces tend to increase with increased molecular weight. So if you're getting 4 samples or 5, AP always has A through E for answers. You pick which one has the highest molecular weight. How do you do that, Rachel?
You memorize the weights.
You look at the periodic table, or you memorize the masses of all 4 million compounds in the world. All right, one or the other. Okay.
That one.
You'd be like Shola. All right.
Who's Shola?
Shola could do all AP Chem math in his head.
I don't know.
Everything. We haven't even really touched math yet. So he can do it all in his head.
This Shola.
Right? No, Neil can't do it in his head like that. All right. So molecular weight, take a look at the boiling point. Also, let's create this tendency as well. All right, what's the relationship here? What do you see here? As
weight increases.
Xavier, you got a question?
Nope.
All right.
Simply thinking aloud.
So that's another little trend that you can know as well. That could be a simple multiple choice type question. All right. That's a 30-second slide. That could be a question on your AP exam. All right. Larger atoms have larger electron clouds, which are easier to polarize. What does polarize mean? Yeah, I mean, got to know what polarize means.
It's the ability to form a dipole, right?
Correct. All right. So polarize. Remember, if there's not a word that you see that you might not know, we need to know that. Just go, something like that. So we know we gotta go over it. All right. Which has the greatest effect? Dipole-dipole interactions or dispersion forces? If 2 molecules are of comparable size and shape, dipole-dipole interactions will likely be the dominating force. How many molecules have dispersion forces? Say it. All of them. When you get it, what is the most common thing of a dispersion force? Give me an element that would have dispersion force. It's a common one. You just look down there on the last page in a box.
HE.
All right, silver by itself. What else? What?
Diatomics.
Diatomics. All right. So now we're getting outside of single atoms or atoms that bind with themselves. Now we would have something outside of dispersion forces. If one molecule is much larger than another, dispersion forces will likely determine its physical properties. All right, great question. You know, a question, who could think of a question that AP could ask based on that?
Which has the what is the physical property of this molecule?
Looking at the following molecules, as boiling point increases, is most likely due to the fact that the dispersion forces, London forces, dipole-dipole, ion-dipole induced physical properties. A boiling point, a melting point. What else? What other physical properties do you people know?
State of matter.
Shape.
Color.
Physical properties.
Electronegativity.
So I'm hearing a lot of good ones. State of matter, those are good ones. Boiling point, melting point. All right. Yeah. All right. This question is always some type of graph relating to this on AP. Okay. The nonpolar series SNH4 to CH4 follow the expected trend. Well, why do you think they're following this trend?
Because they're getting bigger.
I'm getting nervous. Huh? Why?
Because carbon is smaller than SN.
Why is water quite an anomaly?
Because it's polar and has hydrogen bonds.
All right, so water in this case is forming a lot more hydrogen bonds than the others. All right. H2TE, hydrogen telluride, not forming many hydrogen bonds. All right, but more than hydrogen sulfide and hydrogen selenide. Okay. What about the bottom? What's going on with methane through tin hydride, tin 4 hydride?
They're gaining weight.
All right, gaining weight. Okay, so those are your. So what does that mean? How does that relate? I know that's the answer, but what is that? What does that mean?
The higher the weight, the higher the boiling point, or the amount of bonds.
Say it so everybody can hear it and you're not mumbling.
The higher the weight, the higher the boiling point, or the more bonds it can make.
Okay, and the only reason that water is up here is because it has a ton of
Nitrogen.
hydrogen bonds and it's very, very polar. All right, that's the difference. All right. The dipole-dipole interactions experienced with H, when H is bonded to F, N, or O, are usually unusually strong. We call these interaction hydrogen bonds. All right, hydrogen bonding arises in part from the high electronegativity of nitrogen, oxygen, or fluorine. All right, we know those values to be 3.0, 3.5, and 4.0 on the electronegativity values. Hydrogen bonding is what makes your world exist the way it does today. All right, without hydrogen bonding, your world would not be the same. You would not have water the way it is. You would not exist as you are because your DNA is held together by hydrogen bonds. Right? That's how important hydrogen bonds are. Remember, if you can make a weapon that disrupts all hydrogen bonds, you can probably hold the world. Dr.
Sounds like a
Evil.
horrible idea.
Great idea for a movie.
Yeah, but that's someone's action. You should be directed.
I mean, it's like, oh, I have my little weapon, and I point at Allie, and all her hydrogen bonds get disrupted. She just goes into an amorphous blob of nothing. Pretty cool, huh? But her bones would still be intact because they're not held together by hydrogen bonds. So basically,
the
everything
rest
else
of-
just fall off her bones.
Including muscles? Are those very good?
What's that?
Are muscles put together by hydrogen bonds?
Yeah, the water weight. You have 90% water. Okay.
So it's-
Also, when hydrogen bonding is bonded to one of these very electronegative elements, the hydrogen nucleus is exposed. You should know that it's pulling the electrons away, leaving the partial positive charge on hydrogen. We have done that. Oh, we got some angstroms in there. Summarizing intermolecular force is something to memorize. Something to memorize. All right? Interacting molecules or ions. How do you know what it's going to have? What intermolecular force it's going to have? Are polar molecules involved? Yes. Are hydrogen atoms? No. Dipole, dipole. This is how you get your multiple choice questions right. This is it. Right here. All those examples are the typical examples that you're going to see used all the time. Memorize this. All right, intermolecular forces that affect many physical properties. The strength and attractions between particles can greatly affect the properties of substance or solution. All right, this is giving this liquid the ability to have buoyancy, something that can go on the top of the water, a boat. You know, have you ever seen how large boats are that can go on the water? My old man's down in Fort Lauderdale. He said that there was a 320-foot yacht that was down there. That's pretty big, $30 million yacht. That can stay on water, ability to float. That's because these molecules are attracted to each other, creating the tensile strength of the water. If you were to jump down off of the Chesapeake Bay Bridge and the water didn't have any waves, what would happen to you? It would sound like that. You ever do a belly flop and nobody's in the pool? Does it hurt more when people are in the pool or when there's nobody in the pool?
Nobody.
Right? It's like hitting cement. All right? So if you go off the Chesapeake Bay Bridge, there's no waves, there's no water movement, you hit this, you're going to shatter. If there's waves, you have a chance to survive. There's a big difference because it's breaking the particles. All right? This is like cement. All right. Viscosity. We always talk about resistance of a liquid and flow is called viscosity. You should sometimes hear those commercials about viscosity breakdown and making your engine have sludge in it. That's why you should use STP motor oil or whatever it is. That changes the amount of the viscosity. Take a look at this lovely chart here. What happens to viscosity as the substance increases in molecular weight?
It decreases.
It what? It increases. Molecular weight increases, so does viscosity. All right? It is related to each of these. It's related to ease. We pass each other. Viscosity increases with stronger intermolecular forces and decreases with higher temperature. That's what they're talking about when your car engine's running hot. Your viscosity breaks down. Okay? Makes it a lot slower. Surface tension results from the net inward force experienced by one molecule on the surface. A water skipper, large extreme cruise ships can all float on the top of the water due to surface tension. But this is the reason why. The net inward force experienced by molecules. All right. Phase changes. We're going to get into those triple point graphs now. Is there anything there that you don't know?
Deposition. I didn't know the name of that.
What happens for deposition?
Gas to solid.
Gas directly to a solid. There's one that you don't know, jot it down. Solid directly to a gas, sublimes. Great band, Sublime.
From what time period?
Never heard of Sublime. What controls whether it goes directly from gas
What
to
type
solid
of
or
music
gas
is
to
it?
liquid to solid?
Where, here to here?
Like what's the difference? Why would one molecule
What time period?
go from gas to liquid and another go to gas to
It
solid?
depends on their individual temperatures that they exist at. Liquid nitrogen, not liquid nitrogen, solid nitrogen goes directly to gas because it just passes through that phase because of the amount of energy that's transferring. There's not a particular rhyme or reason. It just depends on what the actual element is. Energy changes associated with changes of state, heat of vaporization, heat of fusion. We do have a worksheet that you picked up that we're going to be doing here in just a couple minutes. Heat of fusion. Energy required to change a solid at its melting point to a liquid. Heat of vaporization. Energy required to change a liquid at its boiling point to a gas. Vaporization, and fusion. All right, we're going to calculate those. All right, take a look. What is the relationship on this graph? Take a look. Somebody tell me.
As the heat of vaporization increases, the heat of fusion increases.
As what?
As the heat of vaporization increases, the heat of fusion increases.
All right, but why?
The molecules become smaller. Or the compounds become smaller.
The what?
There's like less elements.
Ah, thank you. Very good. You get one of those today too. Less elements. All right, or atoms. I could say atoms.
What just happened?
All right. Very good. Why?
Because the bonds are stronger.
I just changed it for right here. But why? Why do you think? Why do you think? We have less elements. That makes sense. Kind of, a little bit. There's a lot of elements in the, what we got here? 10, 12, 13, 15. Okay. Close to that. What else? Less. All right, less. Equal what? No, more, look.
Oh yeah, like more.
More. All right, more. All right, very good. All right, energy change associated with a change of state. This graph, you should all have seen before, I would hope. The system added at the melting point, boiling points goes into the pulling of the molecules farther apart from each other. All right, so what is the state of matter right here at A?
Solid.
Solid, and what's happening right here?
It's heating up.
All right, so it's heating up. What is happening right there?
It's plateauing as it melts.
It's melting or freezing. Could be doing either. Could be going either way. Remember, you can go up or down on this. It's not one way or another. What is this? It's liquid. Heating or cooling. All right, because this graph, remember, can go this way or it can go this way. It doesn't matter.
Is it boiling at that point? Or does it not boil?
No, it's liquid.
Not till it's
All right, this could be heating or cooling too. All right, what happens right here?
It's condensing.
Boiling or what?
Condensing. Put it evaporating.
And right here.
It's gas.
All right, gas is heating or cooling, depending on which way you go. Now, there's calculations associated with every part of that graph. All right, there's calculations depending on if it's water, if it's bromine, if it's mercury, whatever it may be. So now, what would we put here? Delta H of what?
Vaporization.
Vape. What would we put down here?
Delta H of fusion.
All right, so at those points, that's where we're going to be using the delta H of fusion value and the delta H of vaporization value. Guess what you use on the other parts of the graph? Right here,
Q equals MK.
right there, and right there.
She's right.
Q equals MC delta T. Very good. Pat yourself on the back.
Do it. Have yourself a bad question. It wasn't me, I didn't say it.
Who said it?
It was totally her.
What? I'll pat myself on the back though. Never pass it down.
Feels good.
Garrett, pat her on the back.
I think yours on
The temperature of the substance does not rise during the phase change. All right. Okay, so now, hold on. We're going to do our worksheet.